Hello everyone, this is Joe. Welcome to my channel. Today we'll talk about the color maps. This is a very useful tool to simplify the Boolean functions. Just as I mentioned in some previous videos, uh, there are plenty of reasons we need to simplify the Boolean functions. The first one is that the simpler the function, the easier it is to realize use circuit. Second, either circuit or simplified circuit means lower cost. Okay, and this means that we can minimize the number of elements in the circuit. And finally, also not it's last but not least, minimize the levels of gating means that we have less delay in our circuit. In another word, our circuit is faster. And our simplification goals is as to reach the minimum SOP or minimum POS forms. Basically, they are the SOP or POS forms that has minimum number of terms and the minimum number of literals. And also we know that both SOP and POS, they are two-level gate circuit. So the simplification, basically we wanted to get a minimum two-level gate circuit with minimum number of gates and gate input. That's our goal. For example, say we have a Boolean function written in the midterm list format. If you recall what we talked about in previous lecture, right? The midterm list format. So it's a format easy to understand, but it's usually not the simplest format. So we can, using the theorems and the laws we learned before, to simplify it. And the most important law we will use for simplification is that x or x prime equal to 1, if you remember this, and also x and 1 equal to x. Okay. So using these two laws, basically we can do some simplification like this one. The simplified circuit is like this. Okay, and similar thing for POS, we can do simplification like this. However, the drawbacks of using the theorem and laws directly to the expression to do the simplification is that for complicated Boolean expressions, it's very hard to know when we get the minimum. And also, in many cases, it's easy to ignore some of the terms that can be simplified. So is there a better way to do the simplification so we won't missing any terms or missing any possible simplification terms? To solve this issue, people invented the color map method. This is a graphic tool for finding the minimal SOP or POS simplification of a Boolean expression, and it's named after its inventor, the American physicist Maurice Karnaugh. Okay. On the right, just to show you some examples of the color maps. So the first one is the map used for one variable system. So there are only two boxes here, and for two variable have 4, 3 variable have 8, and the 4 variable have 16 boxes. Okay, so basically it's a graph to look like this. You can say it's a table or just a combination of boxes. So now let's look at the details. In order to use a color map, the first step is to fill the map, fill the boxes with the correct output value. So here I put the examples for 2, 3, and 4 variable systems. Okay, let's have a look how we can translate from the truth table to the map. Okay, so we start with the 2 variable system. We have this line over here, and so we can put the variables on the 2 sides of this line. So in this case, we have input variable a and b. So you can put a and b here. Basically, the 0, 1 stand for the possible values for each variable. Okay, and you can think this is a coordinate system. So we have the x-axis, which is b, 0, y, 0, 1, and we have the y-axis for a, which is 0 and 1. Okay, so we can define any box using the x and the y number. So like the first box is a 0, 0, so corresponding to decimal 0. Okay, the second here, because a is the MSB in this case, so we got 0, 1, so this is 1, box 1. Then 1, 0 is box 2, 1, 1, box 3. Okay. However, if we write the variable in a different way like this, so this is still 0, but now 0, 1, this will be 1, and this will be 2, and this will be box 3. Okay. Then we just need to fill out each square or box with the corresponding y values. So for box 0, of course, we need to put y0 here, either 1 or 0. Whatever value we have there, we should put it in. So this will be y1, y2, and then y3. In the other case, we have y0, y1, y2, and then y3. So that's how you fill the Karnaugh map or the K-map with from the truth table. Okay, for the 3 variable system, we do similar thing, but since we have 3 variables, so on one side of this line we have 1 variable, the other side we would have 2. See something like that. Then for the x-axis we have 4 combinations, right? Because we got 2 variables, so 4 possible combinations. And for the y-axis, we still have 2 because only 1 variable, 0 and 1. But something you must be careful is that the K-map using something called grain code. We will talk about what is a code later on, but here what we need to know is that for the grain code, the feature is that the adjacent values of the variable can only have 1 bit of difference. For example, the first value is 0, 0, second is 0, 1, so only the LSB is different, the MSB is the same. So that's called only 1 bit is different. Then if we compare 0, 1 and 1, 0, the MSB is different, the LSB is also different. So we have two differences. Then we cannot put them together. Instead, we put 1, 1 because 1, 1 and 0, 1 they only have 1 bit that is different. Also, 1, 1 and 1, 0 only 1 bit is different. So that's why we have to put it this way. Okay. So that's the property of the grain code. You must do it this way, or you won't get correct answer. Okay. So then still do similar thing as the 2 variable system, 0, 0, 0, that's box 0 or square 0. This will be 1. Then 2 will be here because this is 0, 1, 0, that's decimal 2. 0, 1, 1, 3 will be here. 1, 0, 0, 4, 1, 0, 1, 5, 1, 1, 0, 6, 1, 1, 1, 7. Also, maybe we can write this in a different way, something like that, A, B, C. Okay, so you have the free choice to to decide how you want to put the variables yourself. But if you put it different than mine, then you need to be careful how to number the squares. So in this case, we get 0, 0, 0, this is 0, 0, 0, 1, this is 1, 0, 1, 0, this gotta be 2, 0, 1, 1, this gotta be 3. And 1, 1, 0, you will have 6 here instead. And 1, 1, 1, you will have 7 here. 1, 0, 0, have 4 here. And 1, 0, 1, have 5 here. Okay, this is a little messy, so probably you want to do it this way. So then we know how to fill out with the y values. So this, you will put a y0 here, y1 here, y2 here, y3 here, y4, y5, y6, y7. For this one, you must be careful. So here is y1, y0, y1, y2, y3, y4, y5, y6, y7. Okay, so that's how you translate from truth table to Karnaugh map. For 4 variables, similar thing. If we write the variables, we have 4 variables here. So if we write them as this, so now for both x-axis and the y-axis, we have 4 combinations. And still, you need to follow the green code. So on x-axis, after 0, 1, you must put a 1, 1 instead of 1, 0. Same thing on the y-axis. After 0, 1, you need to put 1, 1. Okay, then this square would be 0, 1, 2, 3, 4, 5, 6, 7. Now 8 is here. 9, 10, 1, 0, 1, 0, 10, 11, 12, 13, 14, 15. That's how you write it. You just put the corresponding y values in. Okay. Also, you can write AB on top and CD at the bottom. So AB on the x-axis. Then just need to change this a little bit. So this is y0, y1, y2, y3, y4, y5, y6, y7, y8, y9, y10, y11, y12, 13, 14, 15. Okay, so basically that's how you translate it. And I only stop here at the 4 variable system. You can do similar thing to 5 and 6 variable system, but this thing is very hard to simplify the 5 and 6 or even 7 variable system manually. We can do it using computer, but it's really difficult to do it manually. So for manual simplification, we just use up to 4 variables. Okay. So sometimes if we don't have the truth table ready, but if we have the Boolean functions in either min terms or max term list form, we can also directly translate them into the Karnaugh map. Here is how. For example, if we have this function in min term list format, so basically what we know is that each min term corresponding to the output where its value is 1, right? So all we have to do is to find those min term number in terms of the square numbers, then put those square to be 1. Okay, If you still remember how to count, so if I have this A, B, C, D, so this will be 1, 2, 3, 4, 5, 6, 7, 8. Oh, sorry, I totally messed up. Shouldn't start from 1, we should start from 0. 0, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Okay, so just find the corresponding number. So 0, put 1, 3, put 1, 5, put 1, 7, put 1, 10, 11, 14. Then the rest should equal to 0. So that's how you feel it. For the max term needs to form, we also just need to find the corresponding squares, but put this time we need to put 0 because each max term corresponding to the function value to be 0, not 1, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. So after you get familiar with the map, you don't have to list the number every time. Here I just show it to you so you understand how I figure out the values. Okay, so we find a 1, put 0, 2, 4, 6, 8, 9, 12, 13, 15. The rest should be filled with 1s. Okay. Okay, after the translation, we are kind of ready to do the simplification. But before I explain to you the steps to simplify, we first need to understand an important concept in color map. That's the adjacent or neighbor squares. Okay, neighbors basically we know that is something beside. So neighbor square mean you will think it's a square just beside the square we're talking about, right? But there are kind of a little bit more than that. So let's look at the examples. So say first we have a two variable k map. So we have only 4 squares here. And for each square, we will have only 2 labels. Okay. So if we look at square 0 here, the label would be 0, 1 and 0, 2. 0, 3 is not labeled. So here's how the label is determined. We say the 2 squares are labels when there's only 1 bit difference in the input variables. For example, for square 0, the input combination is 0, 0. For square 1, the combination is 0, 1. So only this bit is different. That's why they are labeled. Similarly, for square 0 and 2, they only have this bit different. So they are labels. However, if we compare 0 and 3, for 3 the combination is 1, 1, 0 is 0, 0. So both bits are different, so they are not labeled. And if we apply this to any other squares in this map, you will find we can conclude that in a 2 variable system, each square has 2 label or adjacent squares. Okay, no matter which one you look at, you can only find the 2 adjacent squares. Okay, now in a 3 variable system, let's pick an easy one, say square 7. Okay, we can find 3 labels for it, like square 3, square 6, and the square 5. Again, if you check either two of them, you will find they have only 1 bit difference, right? So like 7 and 5, this bit different. 7 and 3, this bit is different. 7 and 6, this bit is different. They only have 1 bit that is different. That's why they can be called labels. Okay. Now the special case comes if we look at square 0, how many labels it has? It's very easy to tell that square 1 and square 4 are its labels, right? Only 1 bit difference, right? But if we look closely, we actually find that square 2 is also a label of square 0. Why? If we check the input combination, this is 0, 0, 0. For square 2, we got 0, 1, 0. So only this bit is different. So they are still counted as labels. And this is called wraparound. So wraparound label. Okay. So that's this special thing about this. And this is very important. For the for variable system, then we can think that each square should have like 4 labels. Like for 15, we have 7, 14, 11, and 13. Okay. And the wraparound also exists. For example, for square 12, it has a label 13, label 4, label 8. But don't forget, square 14 is actually the label of 12 because the combination 1, 1, 0, 0, this one 1, 1, 1, 0. Only this bit is different. So they are still labels. So 12 still have 4 labels. And if we look at these squares at the corner, like square 0, okay, we know square 1, let's use a different color. Square 1, not a good one. Square 1 and 0 labels, square 4 and 0 labels, and we have 2 wraparound here. So first square 2 and 0, they are labels. And then square 8 and 0, they are also labels. So we can conclude that for the 4 variable system, each square has 4 labels. Actually, if we expand this to an n variable system, each square should have n adjacent and labeled squares, including wraparound labels. Once you understand the adjacent labels or adjacent squares or labels squares, then we are ready to do the simplification. Now let's look at the steps. So the first step is to count the number of adjacencies for each square with output value 1. Oh, by the way, this step I'm showing here is for getting the minimum SOP expression. We will talk about POS later after this. Okay. So whenever we talk about SOP, we know that we are looking at squares with value 1. Okay, so the first step is count the number of adjacencies for each square with output value 1. So we find the square with 1 there, count how many labels that also has value 1. Okay, then we pick this square with fewest number of adjacent ones. So we know, like, for a 4 variable system, each square has 4 labels, right? But some labels has value 1, some label has value 0. So we only look at the ones with value 1 there, and we pick the one with fewest number of ones that's adjacent. Then we should draw a curve to cover it and its adjacent squares whose output values are also 1 to form a group. So step 3 is to use some drawing to form a group. And something must be satisfied in that group. The first thing is that the number of squares in this group must be the power of 2. So you can have a group covering 1 square, 2 square, 4 squares, 8 squares, or 16. Cannot be any other number. Must be the power of 2. Okay. Also, you need to make sure the group you draw is the largest group you can make for that square. If you can cover 8 squares, don't cover just 4 or 2 or 1. Okay, don't do that. If you do, you will get a redundant term in the result, and you are not getting the minimum expression. Now let's use some example to see what do I mean. Okay, so let's start with this simplest case. Say we got 2 variable column map, and the truth table is translated as this. So to group them, we first check the squares with value 1. And it doesn't matter which one you choose because they are kind of same here. So what we say we start with this one. So following the previous slide, I will check the label squares that whose value is also 1. So only one label. This label has also value 1 there. Then I can make a group to cover these 2 squares. So basically means I can simplify these 2 squares. We will talk about how to simplify later. Here we just focus on grouping. Okay, so we can put these 2 in a group, and this is a group of 2 squares. I can't make anything bigger, and you cannot group 1 squares like that. According to the requirement, we have to make it as big as possible. Similarly, for the 3 variable system, say we have the truth table like that. Okay. In this case, we can, if we check this square first, it has 2 labels that whose value is 1, right? And we also found that these 2 squares are labels, these 2 squares are labels, these 2 are labels, and this is also the label of the first one. So they label their relation kind of forming a loop, right? The next square is the label of the previous square. Even for the last square here, it's the label of the first square. So they're forming a loop. In this case, we can make a group of these 4 squares together. And do not make 2 and 2, something like that. We have to make the biggest one we can make. Okay. Finally, for the example of 4 variable system, say I have something like that. I always give kind of simple example here to show you the basic idea. We will talk more later on. Okay, in this case, we have, let's say we look at this square here. So they have 3 labels whose value is 1, right? And if we check the label relation, these 2 are label, 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 these 2 are label. Again, they are forming a loop here. So the last one here is also the label of the first one. Then which means we can group the 8 squares together. Okay. Don't make group of 4 or 2. You have to make the biggest one. Okay. So after you make the first group, you just need to repeat step beyond. So basically, I mean step 2 and 3. so the typo, until all squares with value 1 has been covered. So you need to repeat the process until you group all the squares whose value is 1. Okay, but that's not the end. You still have one more step to check your groups. Make sure in each group at least one of the squares is not covered by any other group. What do I mean? For example, say I have a K-map look like this, and I did the grouping. So I got 2 here, 2 here, 2 here, 2 here. Then I found, okay, I can also do a 4 here, right? But if you check this yellow group, each square in this group kind grouped in some other groups, right? They are used in other groups. So this group is going to be a redundant group. This will end up a redundant term in your result. So you should not group this. Okay. For those 4 groups, they already covered all they want, so you don't need to do that. And similar case happens here, also in the yellow group. Each of its square is grouped in some other groups, right? Like these 2 in this black also. This one even in 3 groups. This in black, yellow, and the green. These 2 are also in the purple ones. So all of its squares are used by some other groups. So which means this group is redundant. We don't need it. So the grouping is a very critical step, but once we have done that correctly, then we are ready to generate the simplified product term or the minimum SOP term format. Okay, so in order to do this, first we need to check each group and compare the input variable for each square in that group. Keep the input variable whose value do not change, but abandon the variables whose value changes. Then, if the value of the sustained variable is 0, write it in complement form. If it is 1, write it in choose form. Finally, collect all the simplified product terms using all functions. Okay, still it's hard to understand just by reading this. We will use an example to explain it. Okay, let's use these 3 examples to show a complete procedure, how to do the grouping and simplification. So let's look at the first one. So first we will do the grouping, starting with most isolated squares. So I will say either this one or that one. So let's start with this one. So this one has 1 label equal to 0, or 2 label. This is a wraparound label, right? 2 label to be 0, only 1 label is 1. So what I can do, the first group, I've grouped these 2 squares. And for this one here, also has 2 label to be 0, only 1 label is 1. So I think we can group these 2. Then I have another square is left behind. Most of you may naturally think I can just group it by itself, right? But if you do that, you are wrong, because you are not making the biggest group you can make. Okay, because we can find either this square or this square, they are both the label of this one, and their value are 1. So which means you can make a bigger group, like either do this one or either do this one. They are equivalent, but you can only pick one. You cannot do 3, 2, neither, because we said the number of squares in the group must be the power of 2. So you can do it this way. Okay. And check the groups we make. For each group we make here, we have at least one square does not belong to any other group. So this is the right grouping. Then let's try to write the Boolean function, the simplified function. So you can use f or y depending what's the output variable. So let's use y here. So y equal to, first we check how to write this first group. So when there are 2 squares here, and we check each square, the input variable of each square. So for this one we got 0, 0, 0. For this one we got 1, 0, 0. So only a is different, right? So for the variable whose value is different, we abandon it. So we take it out. Basically we only have b and c. And b equal to 0, c equal to 0. So we should write it as b prime or b bar and c prime or c bar. So that's a simplified term for these 2 squares. Actually, you can find out why we take out a. Again, basically we are using the law of this, right? So we can take it out. And for the second group, check the input variables for each square. For this one we got 0, 0, 1. This one we got 0, 1, 1. So only this bit is different, which is corresponding to b. So we will take the b out, only have a, and a equal to 0, so we put a prime, and c equal to 1, so we just put a c. And for the last group, this group here, a is different, bc is not changing, so we will write b and c. Finally, we collect them together using OR function. So that's the simplest SOP form we can get for this one. Have some idea now? Okay, if you're still confused, let's try more examples. Say we have a four variable system like this. So first, let's grouping them. Checking the squares with value 1s and find the most isolated one. Say, I will say this one because it has one label to 0 equal to 0, and it has 1, 2, 3 labels to be 1. And in this case, because these guys are label of each other, and don't forget the wraparound label. So actually, I can tell that I can group the 8 together in this case. They are labels of each other. So I can make a group of 8 instead of 4 or 2. Similarly, I can make a second group of 8, like here, because these 8 squares, they are labels of each other. And in order to write the output function, so we check the blue groups. In the blue groups, the a value is changing, b is not changing, so we have b prime. C is changing. Also, D is also changing. Okay, which means we only have one variable left, which is b, and write as b prime because b equal to 0. For the green group, similar, both a and b are changing. C is changing, only D is not changing. So we write D here using OR function. So we got y equal to b prime or D. Okay, so the last one is a little bit more complicated, but we still follow the same steps. First, try to figure out the most isolated one here. So maybe this square. So two of its label is 0 and the two other labels are 1s. And for this one, there's not much choice. I can only do a group like that. Oh no, actually this is not correct. What we can find is this is the label of this one, but it has a wraparound label here, and this is the label of that, and this is a wraparound label of this, and these two are also labels. So these four squares are label of each other, so we should group them together here. And then let's check this one here. Also, we can find that these four squares, they are label. They are also forming a loop. So we should group them together. Then the output equation y should equal to first check the blue group. So in blue group A is changing, and if we compare this two square, we know that C is changing. So we only have B and D left, and the B equal to 1. So write B. D equal to 0, write as D prime. For the blue, for the green one, if we compare these two squares, we can see B is changing. So A will be there as A prime. And compare these two, we know D is changing, so we have C here. So the final result is B and D prime or A prime C. Okay. The simplification of POS is very similar to SOP, but also there are some key differences. First, in step 1, instead of looking at squares with value 1, we look at squares with value 0. Okay. Similarly, we find the label cells of the one we look at and count how many labels also has 0 in it. Then we do the grouping, follow same requirement. So the number of squares should be the power of 2. And make the largest group you can. Then repeat steps 2 and 3 until all the squares with value 0 has been covered. Then you need to also do a check of your group. Make sure in each group at least one of the squares is not covered by any other group. Step 6. In order to generate a simplified subterm, this time you need you still do similar thing. Compare the input variables for each square in that group. Keep the variables whose value do not change, but abandon the variables whose value changes. Okay. Then, if they keep the variable's value is 0, now this time write it in choose form. If it is 1, write it in complement form. Okay. And you should use all function for that term. Okay. Finally, collect all the simplified subterms using parentheses and add function. Okay, here is also an example to show you how the previous slide works in real problem. But first, let's try to solve this 3-variable question using SOP first. Okay, so if we want to generate SOP expression, we can do a group like that with 2 and another group of 4. And the expression would equal to, for the blue one, we will get A prime C. For the green one, we will get, so B is not changing, so just B. Okay. Now let's try it again with POS. So for POS, if you recall, we need to look at the zeros, not one. So there are only 3 zeros. And also find the most isolated one. So this 0 has a label equal to 1. And the second label also equal to 1. The third label equal to 0. So there is not much choice but to group these two together. And also we can group these two together, follow the same criteria for the grouping. Now to write the POS for the blue group, again we check which variable is changing, which is not. So here B and C are not changing, and B equal to 0, C equal to 0. So this time equal to 0 we should write in choose form. So this equal to B or C for the blue grouping. For the green group, A is not changing, but A equal to 1, so we need to write in complement form. So A prime, or, and the B is not changing, C changed, B. Okay, so that's the result. And if we do some transformation for the result we got here, say first we open the parentheses, we got A prime B, or B and B, or A prime C, or B C. And apply the laws we learned before. So this is B and B should equal to B. A prime C or BC. So we will see that these 3 terms all have B's. So combine them together, use distributive law. So we get A prime or 1 or C or A prime C. So we know this thing in the parentheses equal to 1. So this just equal to B or A prime C. Basically this is the same result as SOP. So we prove that they are equivalent. Okay, now let's look at the 4 variable system. This is also the same problem as shown before, but this time we do POS. Okay, so basically you know that for a given K map, we can always get 2 equivalent results, one in SOP and the other in POS. So for POS, we look at the zeros. So the first thing I can think is that I can group this 4. And then I can group these 4 color ones because they are all wraparound labels of each other, if you recall. And for this one here, because all of its label is 1, so there's no choice. I can only group it by itself. Then if we write the output, again, maybe I use a different color. So the output Y, let's write the green group first, because for the green group only 1 square, so nothing gonna change. So we just write down as A prime, because A equal to 1, or B prime, or C, or D prime. Okay, so no simplification for the first group. For the blue one, we can check that in those 4 squares, A is changing, so take A away, keep B, and write as B, because B equal to 0. And C is changing, so take out C, but leave D. D also equal to 0, so put D here. Then finally for the red group, in red group, both C and D are changing, A and B are not changing, so we put A or B. Okay, you can also try to verify that this is equivalent to the SOP format as shown before. Finally, let's look at the case where we have don't care state. Since the value of those squares doesn't matter, so we always choose their value that can help us with the simplification. For example, in this K-map here, if I want to do SOP, okay, so I will take some of those x values to be 1 and some to be 0, depending which way I can make the biggest group. So let's start with the most isolated ones. So this one has 2 0 labels, but it has one label that equal to 1 and the other label equal to x. So the biggest group, when I look at this, I can actually make a group of 4 if I treated these 2x as 1s. Okay, but the one thing you need to be careful is that once you pick the value for the x squares, then you cannot change it. So if I pick them to be 1 here, then they will stay as 1. Okay, and for this one here, also I can do a group of 4 like that. So basically treat this x as 1 too. Then for these two ones here, a natural thought is to make a group of 2 like that. But that's not the best result actually. If we look at the squares that adjacent to these two, they are all x. So if we pick them all be 1, actually I can make a group of 8. That's the simplest result I can get. So in this case, basically I make all the don't care states equal to 1, because that gives me the best result. So write down it. So for the red group, we have it equal to A. For the blue group, we have B and D. For the green group, we have B and C. Okay, so that's the result for this one. Now another example. So here we only have 4 ones here and the 5th here. So let's start from this one. But actually we can see that if we make those x to be 1, I can directly make a one big group to cover all the ones. Then for the other x, I simply make them to be 0. There will be no issue. Then I got the simplest result, the y equal to d. So you get the idea? We can also do this for the POS. Now I want to do POS. I have 5 0 here. For this 0, if I pick this to be 0, it actually won't help much because I only have 3 squares in as label of each other, and we cannot make a group of 3, right? So it won't help much if I put this as 0. So I can put this as 1. Then I can do a group of this 2, and I can do a group of this 4 here. There's not much reason that to use those x because they are not really helping anything, so we just keep them to be 1. Okay, then we got 2 groups. So y equal to, for this group first, equal to A O C C or D. Then for this group, we got A or B. Okay. In this case, if we take these 2x as 0, we can see that I can make a big group of 8 and also make this 0. And for the others, just make them to be 1 because they are not helping. I can using one group to cover all the zeros. That's the best I can get. In this case, y equal to only d is not changing, so y equal to d. Basically, same result as SOP. Okay, so that's all for Karnaugh maps. Yeah, I know I might be missing some details in this lecture, but I hope I give you a kind of general idea how to use this powerful tool to simplify the Boolean expressions. If you think this is helpful, please help like, share, and subscribe. I'll see you next time. Thank you. Bye.